Good morning, dear students. Welcome to this session on pre-stressed concrete. So we are in Unit 2 of your syllabus and talking about the load balancing concept. Okay. So last session we have seen this example how to solve using load balancing concept. Right. Right. Let us see some other example in this session. A rectangular concrete beam 300 wide, 800 deep, supports two concentrated loads of 20 kilonewton each at third point of a span of 9 meters. So at one third points you have the uh, loads. Let us just draw a rough sketch. So total 9 meters is 9 meters. So make this into three equal parts. So that is what is now the location of loads, right? This is what this mean. Okay, each is 3 meters, right? Now question A, suggest a suitable cable profile. So suitable cable profile for this is trapezoidal, right? If the eccentricity of the cable profile is 100 for the middle third portion of the beam. Okay, calculate the pre-stressing force required to balance the bending effect of the concentrated loads. Okay, so this is the profile that is decided first. So suggest a suitable cable profile means it is trapezoidal cable profile you have to use, and with an eccentricity given 100 okay. Your job is to calculate pre-stressing force required to balance the bending effect of the concentrated loads. So neglecting this self weight of the beam. Okay, so that is a question A. Right. So the answer for that is trapezoidal cable profile is selected because the bending moment diagram due to concentrated load is trapezoidal shape. Okay. Right. So loads given to you 20 kilonewton each. Eccentricity given, span is 9 meters, and accordingly for the given cross section you have to work out the z value, that is bh square by 6. Z is equal to bh square by 6. Okay, where b is 300, h is 800, right? Substitute and get it this 32 into 10 power 6 cube. You need p value, pre-stressing force. Okay, so to balance the the bending moment, what is developed from the load, the moment that is generated from the load is p into e. Okay, so this we have seen when we talk about the load balancing concept. This is how you can see. This is what is p into e shall be equal to W into A into L. Okay, right? So this is what is the equivalent moment or load, whatever, to balance the external loads, right? Okay, so this is the same thing you are using here. Okay, so bending moment due to the load is like this is say Q. This is say Q. Now the reaction is Q. Okay, so bending moment will be maximum under the load. So moment to the left of the section is like Q into 3. Okay, it is like L by 3. L by 3 is nothing but 3 meters. So q into 3, this is q. Okay, length substituted 9 meters, L by 3, 3 meters means here it is L by 3 substituted, and divided by E is 100, so that is 600 kilonewton. Okay, so to balance the effect of load Q, pre-stressing force required value is 600 kilonewton, right? So this is the question A to answer, right? Okay, it is purely from load balancing concept. So to balance the bending moment from the load, what is a moment developed from pre-stressing so force? So P into E is equal to Q into L by 3. This is L by 3, right? So this is how we solve this one. Next, question B. For the same cable profile, find the effective force in the cable, means P value again, if the resultant stress due to self-weight, imposed loads and pre-stressing force is zero at the bottom fiber of the midspan section. Okay, so you are being asked to calculate the pre-stressing force which can create a resultant stress at bottom zero. Okay, so first find out stresses from different sources, like self weight of the beam is cross section into gamma. This is self weight of the beam. So select A into gamma value. Okay, right. So gamma is 24, you know it, and cross sectional area is 300 into 800. It is like 0.8. So correction here in the textbook. So whoever follows the textbook, make necessary corrections wherever they are just typographical errors. It is printed as 9.8. It is 0.8. Okay, so zero point 0.3, 0.8 into 24. Right. So that comes to 5.76. 0.3, 0.8 into 24. So 5.76 kilonewton per meter is the load from weight of the beam. Then bending moment WL square by 8 at center. W. L is 9 by 8 means 0.125. That is coming around 58.32 kilonewton meter. Now stress from this bending moment M by Z. M divided by Z will be giving you 1.82 Newton per mm square. Okay. Now coming to moment at the center due to the loads. Okay, is now this is a bending moment diagram that you can plot it. Okay, so moment is now constant between these loads. So whatever moment you calculated at the under the load is same everywhere. Anywhere you see it is a same value. So even at center it is QL by 3 only. Okay, so that is 20 into 9 by 3, that is 60 kilonewton meter, and stress from that mq by z, okay, is 1.875 Newton per mm square. Now the total tensile stress at bottom is bottom stress is top and bottom both are same. So 1.82 plus 1.87. So to balance this stress, how much is the stress shall be developed from pre-stress? So P is unknown value. So this is stress from pre-stress P by A plus PE by Z at bottom. Okay, so this is again came from P by A plus PE by Z and minus mg by Z minus mq by Z is equal to 0. So this when you bring this to the right hand side, it becomes plus, and left hand side will be having an unknown value of p, and E is given 100, cross sectional area you have cross section given, and Z is calculated. So already these stresses are being calculated. So the total value is 3.695. That means this m g by z and m q by z. It's like m g by z value is m q by z value. So those two, if you add, it is 3.695. Okay, so p, take it out, common, and 1 by cross sectional area, and e by z value 3.695 Newton per mm square. So p will be uh, in terms of newtons and finally converted to kilonewtons by making divided by 10 cube, that is 507 kilonewtons. So 507 kilonewton force is required to make the resultant stress, final stress at bottom 0. Okay, right? Top you will have some value, but bottom stress is 0, which means that tensile stresses are 0 in the cross section. Okay, so this is a solution of this. So just 600 kilonewton is required to balance the load itself by neglecting the self weight. So if you take the self weight also into consideration, we'll be needing 507 kilonewtons to balance the stress, or to get stress at bottom 0, right? So this is how to solve this question. Okay, right, proceed to the next one. So it is for the UDL case, right? So a pre-stressed concrete beam supports an imposed load of 4 kilonewton per meter over the span of 10 meters. So Q value is given, live load value. The beam has a rectangular cross section, width 200 mm and depth 600 mm. To find the effective pre-stressing force if the cable it is parabolic with eccentricity 100 mm at the center. So as you have UDL acting on the beam, you shall select a parabolic cable, even though it is not told, okay, but it is given in the question itself, and 0 at the ends, having 0 eccentricity at the ends for the following conditions. So first question, if the bending effect of the pre-stressing force is nullified by the imposed load for the midspan section, okay, neglecting self weight of the beam. Just if it is only pre-stressing force is balancing the imposed load only, what will be the p value? Okay, the previous question very similar. It was solved for 2-point loads. Now it is for UDL only. So neglecting self weight, what will be p value required to balance UDL? Okay, so to balance UDL, P into E is equal to WL square by 8 is the maximum bending moment at center. So P is unknown, Q value given to you 4, L is a span, 10 meters given. So substitute for L by 8, and E 100 mm, substitute it in meters. So reason Q is in kilonewton per meter. So this is in meters. So this shall be in meters. So that is coming 500 kilonewtons. Okay. So pre-stressing force required is 500 kilonewtons. If you neglect the self weight of the beam, it has to resist only live load. So this much force is required. With no the cable profile, if you just draw it, like this. Just an example. So this is now central cross section. 0 is a midpoint. So 100 mm eccentricity, like if you keep, so you need a parabolic cable profile. Is like parabola. Okay. So this is how you have to take the cable. 0 at the support, 100 mm at center, again 0 to the other support. This is how it has to be uh, cable profile to balance the UDL. Okay, because UDL creates a bending moment of parabolic in nature. Right. What about the second question? If the resultant stress due to self-weight, imposed load, and pre-stressing force is 0 at the soffit, means the bottom of the beam, for the midspan section, what will be pre-stressing force required, P value required. Okay, it's like DC density, in the sense we can also refer it as gamma of concrete. Gamma C is also is the symbol used. Okay, so Krishnaraju used density for D for density, and we are using gamma, general notation of density, right? I mean physics notation, right? So total load, dead load plus live load. So dead load is like 2.88 cross sectional area into gamma, 2.88. Live load is 4, so total 6.88 kilonewton per meter. Instead of calculating individually, you are combining, because anyhow the final stresses, because of both live load and dead load are of same sign, so you can just add them. Okay, because z is same. Okay, sign is same, that's why loads are combined. Okay, so total load, like dead and live load, and moment WL square by 8 from this load. So total load into L square by 8 by 8 is nothing but 0.125, 86 kilonewton meter. So for bottom stresses to be 0, P by A plus PE by Z minus mg by Z minus mq by Z equal to 0, and it is written like mg and mq are combined as just m by Z, minus is equal to 0. So if you bring it to the right hand side, it's m by Z. So P is common, which is unknown. E substitute for 100 mm, cross sectional area, the Z value. Okay, so cross sectional area is 12 into 10 power 4. Z is being 12 into 10 power 6. So M 86 and Z. So P is coming out to be 430 kilonewton. A lesser force is required to make the bottom stress to 0. Okay. So whereas to balance just the live load, you need to have 500 kilonewtons. Okay, neglecting self weight. Right. So this is how we solve the different patterns. If you see, each example is covering a variety of cases. So first case, it was like a point load, single point load. Like next is a, parabolic cable. First one is a triangular shaped cable, right? The third one example is for parabolic cable. Likewise, so each example is having its own importance. Okay, so practice all the example problems given in the prescribed textbook, that is pre-stressed concrete by Krishnaraju, and as well as any other material that is available, which is reliable from the reliable sources, right? Okay, thank you. We'll discuss in the next session some more examples.